So here is a project on predicting kidney disease, if it's chronic or not, which is represented by CKD or not CKD. So that is chronic kidney disease or not chronic kidney disease. So the first thing I did was to get my data, which has all these columns. So obviously these columns are not, relatable because a user might not know what PCV, WC, RBC, what have you. They might not know what that means. So the first thing I did was to ensure data quality assessment by turning all these columns into their right names. So take, for example, RBC now has been changed to red blood cell. SU has been changed to sugar. All right, so now this is my new data frame having the rightful names of the column. And also I took the data and splitted them into numbers and categorical data sets, that is numerical and categorical data sets. So I did that to also to ensure data quality. That is, I needed to see the columns in the categorical columns and the numerical columns that are in the data set. So under the categorical columns, I realized that some columns were being that are numerical columns are being categorized as categorical columns. So obviously, like this now, this is a numerical column, but it's being categorized under categorical columns. White blood cell 2 is meant to be a numerical columns, but categorized under categorical. So is red blood cell count, obviously numerical, but categorized under categorical. So I need to clean up that and process this so they can be classified into their rightful data type. Okay, so I'll do that briefly. So this is a distribution of each of the numerical columns to see if we have a normal or an abnormal distribution. And also this to check for outliers in the data sets. But because this is a classification problem, we are not really affected by outliers. Okay, so this is me cleaning those columns that were numerical, but being categorized as categorical. So this is me cleaning them. So here is the thing. So I found out that in the packed cell volume column, this character we are present in the column, and it's making the column not to be seen as numerical. So I replaced this with nothing. Likewise, replace the none with nothing. So if there be any other thing that I might have missed, then it should be force coerced to numbers using the PD to underscore numeric class. I did that for the remaining two other columns also. Then on to next, preprocessing the missing information in the data. Okay, so I did this to fill the missing information in the data, and here my data is clean. So on to feature engineering. So feature engineering, I encoded and I also scale, but then before I scale, I had to check the standard deviation of the numerical columns in my data set. And I realized that they all had very low deviations away from the mean. So obviously these are low deviations, right? So there's no need to scale because the actual use of scaling is to reduce the distance between the numbers so that we don't have bleedings, So I won't be scaling here, but then I have to encode, that is turn my categorical data sets to numbers because our machines only speak numbers. Okay, so this is me, iterating through the categorical columns. And if the column is inside the data frame, then we instantiate the encoder library and encode the column in iteration. So when it encodes, it saves this encoder so that this encoder can be called and be used to transform feature input data. And here are the encoders that has been saved from this process. Here they are. All right, so moving on. Also, I have about 20-something features. I cannot pour the entire 20-something features into production, so I have to select the best features. So using the the feature importance class of the XGBoost algorithm, I was able to tell what features are the best. So it outlined them on the basis of feature importance. All right, so I selected the columns that the XGBoost feature importance tells me has the most feature importance. All right, so I created a new data frame out of those features, and here is my new data frame saved under the name selected data. All right, so from there, I need to know the number of classes in my Y, in my label, and displaying that, I could see that there's a fictitious class here, which is an error from the input. So I have to drop it out. So when I label encoded this classes column, this CKD was represented with 1. This was represented with 0, 1, and 2. So to remove this, I use the locate, the filter technique to filter out this CKD. So I said select data that locates where this column is not equal to 1. All right, so it returns this two from CKD and not CKD, and I have that here. But then also this might throw issues later, because most algorithms expect the class of 0 and 1, but here I'm having 0 and 2, which might be a potential issue later. So what I do is to convert all the location of 2 to be 1 and non-location of 0 to be 0. So I have the same data but under different names now to align with our algorithms. Okay, so onto the modeling. I split it into train and tests using a train size of 85% and stratifying my Y. So I created this function to run different algorithms for me at a go. So I'm using the random forest classifier, the decision tree, XGB, support vector classifier, the nearest neighbor classifier also. So I'm using these 5 classifiers. Okay, so when it's done, this is the output of the function. This function, this is the output. And yes, I saved. So I kind of sorted this table according to the algorithm or the model that has the least overfitting. Again, I sorted this table according to the model that has the least overfitting. All right. So this is what I'm doing. So model 1 is the first model that has the least overfitting. Model 2 is the second model that has the least overfitting. Okay, so I feed in my X train, my Y train, my X test, my Y test. So basically, this entire function does models for me using all these algorithms. It uses all these algorithms and creates 5 models for me and outputs all the 5 and their prevailing scores. And their outputs is sorted in order of their overfitting. So it's outputting according to the overfitting they have. So if you can see 98 to 1, that's about 2% overfitting. Also, this 2% overfitting, this one is 4% overfitting, and this one is 7% overfitting thereabouts. So the table is sorted in order of the least overfitting. So my model 1 is the first model that has the least overfitting. My model 2 is the second model that has the least overfitting. All right, so as you can see, the model 1, you can see that is the random forest class that has the least overfitting, which is this. And the model 2 is the XGBoost classifier class that has the least overfitting here. All right, so choosing the random forest, I could choose any of them, the random forest or the XGBoost, but then working on with the random forest, just, double checking. So I'm saying the random forest model predicts the X train to see if my data is not, if my model is not underfitting. And as you can see, I have a precision of 100% for the class of 0 and also 100% for the class of 1. So to test this model on a new data set it has never seen before, so testing it, the model that predicts the X test. So I have a precision of 100% in predicting the class of 1 and 96, sorry, a precision of 100% in predicting the class of 0 and 96% in predicting the class of 1. All right, so that's a good model. That's optimal. It doesn't overfit, neither does it underfit. So that makes it an optimal model, and I saved the model. And here is my model, the kidney model. And here is it. And every other one are the encoders. So this can be, used for further production. Thank you very much. And that will be all for now.